Hi, I'm happy to be here and to speak about Morse boundaries of graph of groups with examples of right-angled Artin and Coxeter groups. This is part 1, where we focus on the examples. And this here is a general outline of the both parts. The part 1, we will focus on the examples as I said before. First, we will see some definitions we need, and we will see a theorem which results from my dissertation with applications to right-angled Artin and Coxeter groups. And in the end of this talk, we will see that things work because those groups we study there split nicely as amalgamated free products, where the edge groups do not contribute something to the Morse boundary of the ambient group. And this will lead us then to the second part, where we will see a generalization of this theorem for general graph of groups. So there we will study connected components of Morse boundaries of graph of groups. This is joint work with Elia Fioravanti. And again, here it is essential that the edge groups we study do not contribute something to the Morse boundary of the ambient group. But then in the last part of the part 2 of these talks, I will show you some examples where the edge group contributes something to the Morse boundary of the ambient group. And there we will see that interesting things happen there. And this is related to joint work with Marius Gräber, Neil Lazarowicz, and Emily Stein. Let's start. So what is the goal of this first part of these talks? So say that delta is a graph, then associated to this graph is a right-angled Artin or Coxeter group. And this has an associated topological space, which is called Morse boundary. Now we can glue to delta another graph, and if we do so, the group changes. And we would like to understand what is happening there with the Morse boundary. The Morse boundary was introduced by Chareny and Sultan as a contracting boundary and was generalized by Matthew Cordes to the Morse boundary. It is a quasi-isometry invariant, and this is interesting for us in particular because of the following. If we have two groups, which are right-angled Artin or Coxeter groups, and their Morse boundaries are distinct, then we have that these groups have a distinct large-scale geometry. So the Morse boundary here is a tool to distinguish those groups. Now I would like to explain to you what the Morse boundary is, and for that we have first to understand Gromov boundaries. Because Morse boundaries generalize Gromov boundaries. Gromov boundaries are defined for hyperbolic spaces. A hyperbolic space is a geodesic metric space where there exists a delta such that we have the following for each geodesic triangle. The delta neighborhood of two sides of each geodesic triangle contains the third side of the triangle. And now a group is called hyperbolic if it acts geometrically on a hyperbolic space. And a geometric action is an action which is proper co-compact by isometries. Each finitely generated group acts geometrically on its K-D graph. So what you can have here in mind is just think of X as some K-D graph of G. And now the Gromov boundary of the group is defined as the Gromov boundary of a space on which the group acts geometrically on. And hereby it is not important which space we take. The Gromov boundary is independent of the choice of the space. And the Gromov boundary consists of geodesic rays, where we identify two geodesic rays if they stay close to each other. What means that there exists a constant c, such that the distances of the two geodesic rays are at most c for all times. What is the idea? The idea is that we stand in a point in our space, and we think of like in which direction we can go, and for each direction we think of the boundary point at infinity. And because like finite distances do not matter, we get these equivalence classes here. And we give this space the following topology, like just intuitively, this topology is made this way, that two equivalence classes are close if representatives of these equivalence classes stay close for a long time. So these two geodesic rays, for instance, are more far away from each other than these two geodesic rays. And the typical example is a hyperbolic plane where we get for each direction one boundary point, and here we get a one sphere as boundary. Now let's look what the Morse boundary is. Here we look now at some proper geodesic metric space and look at a group which is now finitely generated, which acts geometrically on such a proper geodesic metric space. Again, here you can just think as one example as a Cayley graph or some Cayley graph of G. And then the Morse boundary of G is defined as the Morse boundary of such a space X, where we now have that the Morse boundary consists of all equivalence classes of geodesic rays which are Morse. And the topology is a direct limit topology generalizing the Gromov boundary. So now we have to understand what Morseness means. A geodesic ray is Morse if it behaves like a geodesic ray in hyperbolic spaces. That means quasi-geodesics with endpoints on gamma stays close to gamma. More precisely, if gamma, like a geodesic ray gamma, is Morse, if we have that each KL quasi-geodesic stays in an M of KL neighborhood about gamma. Thereby, this M depends on the constants K and L. So for instance, the Morse boundary of the hyperbolic plane is a circle. More generally, if we have a hyperbolic space, then the Morse boundary is the same as the Gromov boundary. Like I said before, the idea is that the Morse boundary generalizes the Gromov boundary. And the Morse boundary of the hyperbolic plane, of the Euclidean plane is empty. Why? Like here we see an example. We see this geodesic ray here with the square root 2, 0 quasi-geodesics. And like all these geodesics here are 0, 0, 2, 0 quasi-geodesics. But we see that these quasi-geodesics go arbitrarily far away from this base geodesic ray. And this is not allowed if we have, because we need to find a neighborhood where these quasi-geodesics need to stay close. So this is something what you really should remember. Most geodesic rays behave differently to geodesic rays in Euclidean planes. Let's look at this example here. This group is that the free product of that with that squared. And the Cayley graph is quasi-isometric to a tree of Euclidean planes, what means that it looks like a tree of Euclidean planes if we look from it from far apart. And now, if we have a tree of Euclidean planes, we can study geodesic rays in such a space. We fix a base point, and now we look, for instance, at those geodesic rays which end in Euclidean planes. Those are not Morse, because we saw already that Euclidean planes do not contain Morse geodesic rays. But they get Morse if we stay in each such Euclidean plane only for a bounded amount of time. And like we'd have a uniform bound for that. If we have that the bound how long the geodesic ray stays in the Euclidean plane like grows over time, then this is not Morse anymore. Here's another example. We take the hyperbolic plane. We know already that the boundary is a circle. Now we glue on a Euclidean half plane. If we do so, this bi-infinite line here is not Morse anymore. And so we lose two boundary points because of that. And so the Morse boundary here is a union of two open intervals. So we notice two things here. First, the Morse boundary does not have to be compact. And second, if we glue on spaces, the Morse boundary might become smaller. Now we would like to understand Morse boundaries of right-angled Artin and Coxeter groups. So what are those groups? If delta is a graph, then the associated right-angled Artin group is generated by the vertices of the group, and two generators commute if there is an edge between them. A right-angled Artin Coxeter group, this is this group W delta, is defined similar, but here we add a relation, namely now every generator should be an involution. And if we write gamma of delta, we mean always that gamma can be a right-angled Artin or a right-angled Coxeter group associated to the graph delta. And now, before we come to the theorem, I would like to explain to you, we have to understand what induced subgraphs are. So if we have subgraph delta prime in a graph delta, then it is induced if two vertices in delta prime are linked by an edge, if and only if they are linked by an edge in delta. For instance, this red graph here is not induced because we have these two vertices contained in the red graph, but there is an edge which is not contained in this graph. But this here is a positive example which is induced. Now we are ready to read the following theorem. And the goal of this talk will be to get a feeling for this theorem, like for the consequences of the theorem for right-angled Artin and Coxeter groups. So if we have a graph and we can write this graph nicely, namely as a union of two graphs, so that the intersection graph is induced in delta 1 and delta 2. So that means that we can think of these delta as a result of gluing two graphs nicely together. And we have that the Morse boundaries of the groups associated to the graphs we started with, like if the Morse boundaries of the groups we started with are totally disconnected, and if we have that the intersection graph is contained in an induced subgraph delta prime of delta, corresponding to a group with empty Morse boundary, then the resulting group is totally disconnected. So what is like the flavor of the theorem? The flavor is if we have glue two graphs together in a nice way, then, and we know that the graphs correspond to groups with totally disconnected Morse boundary, then the resulting group also has totally disconnected Morse boundary if the intersection graph behaves nicely enough, namely has this empty Morse boundary condition. And this is what we would like now to illustrate for the right-angled Artin and Coxeter group case. So we start first with the right-angled Artin group case. Let's first understand right-angled Artin groups better. So if we have a vertex, then the corresponding right-angled Artin group is just that, and the Morse boundary are 2 points. If we have vertices, then the Morse boundary is a free group. Sorry, the Artin group is a free group, and the Morse boundary is a Cantor set. If we have an edge, then the Artin group is that to the 2. And there we see just an integer grid. And this is like in the Euclidean plane case, we see here that the Morse boundary is empty. More general, an n click corresponds to that to the n. N vertices without any edge corresponds to a free group. And in the last case, we consider the special case that we look at joins of two graphs. What is a join of two graphs? Like we just take one graph and the other graph and link all the vertices of the one graph with the vertices of the other graph. And if we do so, then we get a direct product of the two Artin groups we started with. And here the Artin groups have always like infinite elements, and the direct product of two infinite groups always gives a group with empty Morse boundary. Now, after we understood this, we will now apply the theorem to understand how we can glue graphs nicely together to get nice information about the Morse boundary of the corresponding right-angled Artin group. So first, we remember that if delta is a clique, then the corresponding Artin group is that to the n, and the Morse boundary here is empty. So now let's assume that delta is not a clique. Then there is a vertex v which is not connected to all other vertices of the graph. Then we can look at the star of v, which is a graph induced by all vertices which are either neighbored to v or the vertex v itself. The neighborhood of v is the subgraph induced by all the vertices in the neighborhood of v. And then we have the remaining graph, which just consists of all, it's just induced by all vertices except for v. And if we do so, we see that we now decomposed our graph in a nice way, namely into the star of v, the neighborhood of v, and delta minus the neighborhood of v. And this is exactly like such a case like we have in the example. Like we can think of that we get our graph by gluing the star of v to delta minus v. And the intersection graph here is the neighborhood of v. And what here is like what we had in the theorem, what we want to have. We want that the intersection graph is induced in delta 1 and delta 2. So here the neighborhood of v is induced in the star of v and in the graph delta minus v. We want that the groups we start with have totally disconnected Morse boundary. We are not there yet, but keep this condition in mind. And finally, we want that the intersection graph is contained in an induced subgraph corresponding to a group with empty Morse boundary. And this is something what is satisfied here. Indeed, the intersection graph is here the neighborhood of v, and it is contained in the star of v. And now the star of v, the right-angled Artin group corresponding to it, is just a direct product of that and the Artin group corresponding to the neighborhood of v. This was this joint condition we studied before. And a direct product of two infinite groups gives us an empty Morse boundary. So here this group has empty Morse boundary, and so we see that this neighborhood indeed corresponds to a group with empty Morse boundary. This is nice because what we do now is that we just repeat the same argument for the right-angled Artin group corresponding to delta minus v. And now we can continue until we arrive at a clique. And again, a clique corresponds to that to the n. So it's like has empty Morse boundary. And so this means that we can now inductively apply our theorem to see that the Morse boundary of every right-angled Artin group is totally disconnected. This is a reproof of a theorem of Chareny Cordes sister. They show something more general, namely they also show what topologies can arise. So they show that there are just four possibilities. Either the Morse boundary is empty, or it consists of 2 points, or it is a Cantor space, or an omega Cantor space. And they characterize exactly when you have which topology. But I think this is a nice way to see like how graph decompositions can tell us something about the Morse boundary of the resulting group. Now let's compare the situation to right-angled Coxeter groups. Here we have that if we have a vertex, then the corresponding group is not that anymore, but that modulo 2z. So we have a finite group here. And if we have two non-linked vertices, then we have not a free product of two cyclic groups, but we have a free product of that modulo 2z with that modulo 2z, and this is isomorphic to the dihedral group. And if we have an edge, we have not a direct product of z with z, but a direct product of z to the 2z with z to the 2z. So we get a scalar graph such a square here. So we get finite graphs here, and this is a very big, like finite groups, sorry, and this makes a very big difference. So if we have a finite group, of course, there are no geodetic rays, and there we have empty Morse boundary. And here in this situation, we see that we have two directions, and so we get 2 points in the Morse boundary. More general, an n-click corresponds to an n cross n cube. N vertices corresponds to an n-valence tree and to such a group here. And again, like in the Artin group case, a join of two graphs corresponds to a direct product. And now if we have that the two right-angled Coxeter groups, like the two factors, are both infinite, then we get automatically, as before, that the Morse boundary is empty. And we have that a right-angled Coxeter group is infinite if we have at least two non-adjacent vertices in our defining graphs. So now, here are two important examples. If we have a 4 cycle, then the Cayley graph looks like a Euclidean plane. And then we have that, like, okay, I mean, it has like an integer grid. And then we have that the Morse boundary is empty. If we have that the graph is a 5 cycle, then the Cayley graph is quasi-isometric to the hyperbolic plane. And then we have that the Morse boundary is a circle. And this is quite important because here we see already that not all right-angled Coxeter groups have totally disconnected Morse boundaries. And this means that there are right-angled Coxeter groups, like if we have a right-angled Coxeter group whose Morse boundary is not totally disconnected, we directly know it cannot be quasi-isometric to any right-angled Artin group. And this is quite interesting because in general, like it's an interesting question, which right-angled Artin groups are quasi-isometric to right-angled Coxeter groups. And now we construct recursively a graph class which corresponds to groups with totally disconnected Morse boundary. First, we put all groups into, like graphs, into this class where we know already that the corresponding right-angled Coxeter group has totally disconnected Morse boundary. So we put in it trees, clicks, and joins of two graphs with at least two non-adjacent vertices each. So here I should maybe mention shortly that the empty set is totally disconnected from me. And next, whenever we have two graphs and the intersection graph is contained in an induced subgraph delta prime, whose corresponding right-angled Coxeter group has empty Morse boundary, then we add the union of the two graphs. Why do we do this? Because our theorem tells us that in this case, that the union of delta 1 and delta 2 corresponds to right-angled Coxeter group with empty, totally disconnected contracting boundary. Here are some examples which lie in this graph. So here, Chareny and Sultan studied this graph, and this graph is very similar to the first graph. And we see that we can decompose this graph into a tree and a join graph, which corresponds to an empty Morse boundary group. And it is has totally disconnected Morse boundary. Another example of graphs which lie in this class C is the following. These graphs were studied by Pallavi and Anne Thomas. They showed with the help of these graphs that there are right-angled Coxeter groups of arbitrary high, of divergence of arbitrarily high polynomial degree. And we can decompose these graphs in this way. So we have, again, trees and joins. And we can also do something like this. We take this graph where we know that it is in C, and we glue such a graph here on it. So this yellow graph is a join, so it has empty, like the corresponding right-angled Coxeter group has empty Morse boundary. And now the yellow and the green graph together correspond to a right-angled Coxeter group with totally disconnected Morse boundary. And so the whole thing in the end is contained in C. Finally, one can also show that this graph here, which was studied by Roussel, Spriano, and Hahn, is contained in this class. So it corresponds to a right-angled Coxeter group this totally disconnected Morse boundary. So now we saw that the situation is quite different in the case of right-angled Artin and Coxeter groups, but in both situations, the compositions of the graphs tell us a lot about the Morse boundaries of the groups. And it's like interesting now to understand why. So what is going on here? The important point here is to notice that if we have such a nice decomposition of the graph, this gives us a nice splitting of the group. So here we have the graph splits as an amalgamated free product of two graphs corresponding to the first and to the second graph along a group which corresponds to the intersection graph. And remember, this intersection graph satisfies an empty Morse boundary condition. And this is the Morse boundary condition on our edge groups I mentioned at the beginning of this talk. And we will learn about this more in the second talk. Thank you.